I had prepared much more material than I was able to cover, so today I had to make some choices. I posted on Slack a couple of references, including one book that has just been released this year, a basic introduction and all kinds of related things. And the book has also a lot of references to more advanced material. Someone asked me about books on category theory. I can also post a list of references if you like, but the main book I usually advise is the book by Steve Awudi called just Category Theory. So that would be my advice for a reference on category theory. What I'm going to do today, so we went from concrete to abstract, and today we'll go back to concrete. And I want to say a few things about semantics and about the notational semantics and operational semantics. And then I want to show you a full worked out example on regular languages and automata. So what we've seen yesterday in a very abstract picture is that if you have a certain functor f, I'm using super size font today. If you have a certain functor f, there exists this special object for many functors called the final coalgebra. Let's call it Z for a moment. And this final coalgebra has this property that for any f coalgebra on this side, there is a unique map into the final coalgebra. And you might wonder, what does this have to do with programming language semantics? So if you think of X as being the syntax of a language, and if you think of F as capturing the small step semantics that you might write for a language, then the existence of a final coalgebra and this map basically gives you a way to talk about the notations of your programs. Okay? This is the connection between final coalgebra and semantics. And so I'm going to give you an example today of the most basic language that I know of. Andrew mentioned IMP in his lectures, and I'm going to go even a bit further back, and I'm going to look at regular expressions as programs denoting regular languages, right? You can think of regular expressions as a syntactic denotation of regular languages. And what we're going to do, I'm going to show you how to give a small step semantics to regular expressions in a way that this picture then recovers what you would see in classical books as the denotational semantics of regular expressions as regular languages. Okay? And a similar thing, exactly what I'm doing here for regular expressions can be done for languages like IMP, which is still a very simple picture, and for more advanced languages like languages with probabilistic constructs. Okay, so this picture is relatively general and can be applied in various places in semantics. Okay, so today we're going to fully work out an example together, and we're going to look at regular expressions and regular languages as an instance of this picture. So to do that, let's just set some notation first. So regular expressions, I'm going to use the following notation. I'm going to use 0 to denote the empty language, 1 to denote the empty word, and then plus concatenation and star. Okay, this is my language. Sorry, my syntax. And my goal is to say that regular expressions are just a syntax for regular languages. So I need to choose an f that magically results in a final coalgebra Z that includes regular languages. Okay? So the first observation, I'm even going to call it a theorem so that Jan pays attention. It's another theorem. Is that if you take f to be the following functor, so A is an alphabet and 2 is the two-element set. So for f this functor, the final coalgebra of f is 2 to the a star. And we've seen this example yesterday, actually. Okay? Proof. So how do we prove this? Okay, first of all, we need to show that 2 to the a star has indeed an f algebra structure. So there is a function from languages to 2 times a to languages. And this function is something that is called sometimes in the literature language derivatives or Brzozowski derivatives. And this is defined as follows. So if I give you a language, I can define 2 functions. So given a language L in 2 to the a star, I can define 2 functions. One I'm going to call epsilon interrogation mark, that basically gives me 1 if the empty word is in the language and 0 otherwise. And then I can define a function delta that takes a language L and then letter A in the alphabet and returns all the words. So first I'm going to write as a set and then as a function. Returns all the words such that AU is in the language. So here I'm using the fact that 2 to the a star is isomorphic just to sets over words. If I were being really precise, I should write this function as follows. So this is just the change between the characteristic function of a set and the set itself. So these things are equivalent. Okay? So using these 2 functions, epsilon and delta, I basically have the set of languages written as a coalgebra for functor f. And now what makes this coalgebra final? If I can show that for any other f coalgebra there exists a unique map into this object. Okay. So we need to basically, given OT on this side, we need to define an H on this side that makes this diagram commute. So we did this for streams yesterday. If you look at the diagram for a little while and at the definition of epsilon and delta, you will start seeing the definition of H. So we need to define h of x of a word u. And so what we're going to do, we're just basically going to break this definition of h into two cases. If the word is the empty word, then I know something about what the diagram does. And if the word is not the empty word, then I also know something by going through the diagram. So, okay, so what's the definition of h of x for the empty word? Everyone is exhausted. If we can't do the base case, then I cannot continue. Maybe I should ask Jan. So, what is h of x of the empty word? So the only thing, so h of x of the empty word, for this diagram to make sense, has to be the same thing as O of x. Because if it is not O of x, then we're already breaking the commutativity. So the only thing we can put here is O of x. And similarly, if the word has a letter A and continues with U, the only way to define h is by doing one step in the automaton with t, and then evaluating h on u. Okay? So to see that h is well defined, you have to observe that it's actually defined by induction on A star. So I define the function on words. And in fact, you can also use induction on A star to prove uniqueness. So this is homework. Okay, but now we can go back to the syntax. So now that diagram gives us a way to do semantics. So now in order to provide semantics to regular expressions, what we need to do, so we have these regular expressions, and the syntax is missing something. Has anyone spotted that? Letters. Yeah. Without letters, this would be a very... Okay, so we have these regular expressions, and we would like to assign to these regular expressions as the notational semantics a language. Okay, we would like to define a map here that assigns to regular expressions languages. So how can we use that diagram to do that? What do we need to do in order to be able to use that diagram?
We need an algebra for...
Yeah, we need to give the regular expressions the structure of a coalgebra or an automaton, and then we can basically use the uniqueness to assign to regular expressions the language they accept. Okay, so we need to define here a structure and this structure is is, you can think of it as a small step semantics for regular expressions, okay? And the definitions I'm going to use here go back again to Brzozowski in the 60s, where he provided an alternative proof of Kleene's theorem associating automata with regular expressions.
Would you mind writing down his name? Just so that I can look it up.
Yeah. Can you read that? Okay. I hope I didn't misspell it. Okay, as I wrote his name here, I'm gonna write the definition here. Okay, so let's define, so we need to define a function from regular expressions to 2, and then a function that goes from regular expressions, takes a letter, and gives me another regular expression. So I'm going to do this in a table, just to make it a bit easier. So we're going to write all the expressions here. And then we're going to write E. And then we're going to write D for a letter A. Okay? So for the regular expression 0, remember that 0 is supposed to denote the empty language. Then we're going to choose to associate 0 with 0. And for any letter, it's going to make a transition to itself. So what I'm going to do to give you an impression of what these syntactic expressions are doing, I'm going to write on the side a picture of the automata that this would correspond to. So for the empty language, this is the automaton that accepts the empty language. It has one state that is not final and loops for every letter. Okay? If I take the empty word, or the expression denoting the empty word, then what I'm going to do, I'm going to set E to 1, but then for every letter, I'm going to set the derivative to 0. So if you draw this coalgebra, what you get is an automaton that looks like this. So you see that that gives you an automaton that accepts only the empty word. If I have an expression that has a letter A, then I'm going to set E to be 0. And here, I'm going to make a case distinction. Let's call this B to make it different. If A equals B, then I'm going to move to state 1. And if A does not equal B, then I'm going to move to state 0. So note that this A here is ranging over the whole alphabet, and this is one concrete letter, B. Okay? So this automaton is going to look like this, if I read B, which is the letter that I'm looking at, then I accept. And if I read A, any other A, then I go to a non-accepting state. So if I have a sum of two expressions, R plus S, then I'm just going to evaluate E on each of them. And then if you think what E means, which is should this state accept the empty word, then in a sum it will accept the empty word if any of them accepts the empty word. So then you can just take this junction of the result of E. And the D, I can just apply D to R and D to S, and then combine the results, which are regular expressions, with the plus. Okay? If I have a sequential composition of expressions, then if you think about the languages that they might be denoting, you will notice that the only way for this to denote the empty word is if both of them denote the empty word. Because otherwise, in the concatenation, you will always eliminate the empty word. So I need the empty word in both. So I just set E to be the conjunction of E of R and E of S. And now, what do I write for the derivative? That is a bit trickier. So what's the intended meaning of the derivative is that I have processed one letter A, and then I keep the rest. So it's like if you write all the traces of this program, the derivative is basically deleting the first occurrence, the A's that occur in the first letter. Now, if I have a concatenation, where can the A's occur? Well, they can appear at the beginning of R. So I can remove the A from R and then continue with what S is doing. But what if R contains the empty word? What happens? Well, then I can skip the program R and I can remove the A from S. So that's the other option, in which I check if R has the empty word, and then I continue by removing an A from S. And I want to take these both, I want to do both. So I want to consider all the traces that come from removing an A from R and all the traces that come from removing an A from S if R lets me continue. Okay? Okay, and last, the star. So R star always contains the empty word. So E of R star is 1. And to remove an A from R star, what I do, I remove an A from R and I continue with R star. So R star is like a while loop that always executes a while through R. So if I can remove an A, it must come from R, and then I continue with whatever traces I had before. Okay? So this table basically gives you two functions, E and D, that provide a coalgebra structure to regular expressions. And that coalgebra structure has the same type of the coalgebra structure we defined just a few minutes ago. And because this is a final coalgebra, we now have by uniqueness this function that assigns to every regular expression a language. Okay? And you can prove that that function there so the function that you obtain by uniqueness, so if you read out this diagram and if you read out what the commutativity gives you, then you will obtain the following. I associate with expression 0 the empty set. I associate with expression 1 the set with the empty word. And note that I'm now, I do this quite a lot, and I hope it's not too confusing. I switch between the characteristic function representation and the sets. Is this bearable? Okay. Okay, and it assigns to the letter A, let's use B, the set with B, and to the plus, the union, and to the star, all the iterations over the words. So you will probably recognize this definition I wrote here as the sort of classical interpretation of regular expressions that you will see in books. And you can show that that comes exactly from this commutativity. Oh, sorry. Great question. Okay, let's do something similar with algebras. So indeed, regular expressions are also algebras. And in fact, there is a very nice picture connecting both the algebraic perspective and the coalgebraic perspective. So let's prove, or let's at least show, that you can recover this definition I wrote here on the board also algebraically. So regular expressions, the syntax of regular expressions, is the initial algebra of the following functor. And let me just draw this a bit lower, otherwise. So if you take the functor 1 plus 1 plus a plus, okay, this is going to be very ugly. Forget about the star for a moment, otherwise I don't have space on the board. So call this functor s of x. So if I write this functor and I define this map as being basically returning me the constant 0, the constant 1, the constant a, concatenation, and plus, and I'm ignoring the star for a moment, then you can show that regular expressions are the initial algebra of this functor. Okay? Which means that because they are an initial algebra, if I am able to put an algebra structure here in languages, then I will recover here something. And it so happens that the something you recover, and I'm going to tell you this definition in a second, is exactly that we just did coalgebraically. And I will say also why it is to mention this definition of this algebra here, alpha. So what alpha does is precisely yes, so this is S applied to reg, sorry. So alpha will associate with one, the empty language, with the other one, the language with the empty word, with A, the singleton language with the word A, and then we'll take a pair of languages and do the concatenation, and this pair and do the union. And if you do that, then you get this unique map, and reading out the commutativity of this diagram gives you exactly the definitions that are on the board. So regular expressions are very special in this way, because you can recover the syntax both algebraically and coalgebraically. And the reason why the maps coincide comes from the fact that this functor S and the functor F that I, in the meantime, have deleted, so the functor F and the functor S I'm writing blanks instead of the variables. They interact in a special way. And I'm not going to say too much about it, but there is a very special natural transformation between the composition of these functors. And this is topic for another lecture. But there's a distributive law between Fs and Sf, and if I am really precise, it's a slight transformation on S in order to deal with the star. Okay, so regular expressions have this very special property of being both algebras and coalgebras in a very precise way. And the functor f is the functor for deterministic automata. And this table that I wrote here, these Brozovsky derivatives, together with the semantic function, together with this final coalgebra theorem, give you an alternative proof of Kleene's theorem that says that if you have that regular of half of Kleene's theorem, that says that if you have a regular expression, then you are denoting exactly a regular language. And I haven't, so this is the set of all languages, so the regularity bit is not yet there, but you can look at the image of this function and show that all the languages you obtain in the image have the property of being a finite automaton. Okay, so there's some very sort of classical results hidden away in this abstract picture. Did I hear a question? To prove that to go from languages to regular expressions? Yes. So let me think for a second how I'm going to answer this question. So to go from languages to regular expressions, what you end up doing is solving a system of equations. And that system of equations can be distilled from the diagram that I deleted. But you can basically look at the derivatives of the languages. Sorry, you start from an automaton. You can look at the languages that it accepts. And then you can look at the system of equations you get from that commutativity. And you will end up with a system of equations that looks like this. Maybe it accepts the empty word, and then for some A, it goes to a state Y, and for some B, it goes to a state Z, and then for Y, maybe it doesn't accept the empty word, and for A, it goes to itself, and for B, it goes to X, and for Z, and so on. So you distill from the commutativity of the diagram a system of equations, and then you show that matrices, so that this system actually also has an algebra structure, and then you compute the solution. So the solutions can also be obtained using very similar techniques. But again, that would be yet another lecture. I mean, there's a lot of technical details to show that such systems have solutions, and it is not for regular expressions and for regular languages. Everything is known, and there's a lot of explanations out there. But every time you have a new language and you need to go through exercise again, doing this step of the systems is usually the hard bit. So showing that the system has a unique solution is the hard bit. Okay, this might be a good point for a break. 5 minutes. Okay, so we got to the part of my lecture in which I'll tell you everything I was planning to tell you in like 20 minutes, and this is like the content of 4 lectures. No, I think what I'm going to do for the next half an hour is go through a list of things that you might want to look at first. Mention some related references. I'll put that on Slack as well. And then the last 10 minutes, I'll show you some old slides on something called CoCaml, and there's been requests in the audience for this. So I'll just show you something a bit different. But before we do that, what I'm going to do now, I'm going to summarize a little bit what we looked at, and then I'm going to give a couple of examples, and I'm going to mention a couple of topics that I wish I had had the time to go through. Okay, so this is the main picture that I hope you can take home, which is for a very general class of types given by G. If you have a coalgebra for G, and you can think of this as a sort of small step semantics in a language, then you can canonically derive its denotational semantics by finality. So this is kind of one of the main messages I hope you got. Now, there was a question during the break, and I think I probably haven't mentioned that enough, is that of course the definition of your semantics is very much dependent on what you choose to put here as your small step semantics. Okay? So for instance, in the case of regular expressions, we had the E and the D table that I wrote here before, and that is a choice I made for E and D because I knew what I wanted to get as a result. But imagine I didn't know what I wanted to get as a result, and I was just sort of using the types as my guide. I could have, in principle, said that for the concatenation, I could keep the same E as I had before, but I could have changed the way I took derivative. So in particular, I could have said that I take the A from S first, and then if S has the empty word, I take an A from R. It's a valid, it's a valid definition. That would so what am I doing by basically taking the A from S there? Exactly. I'm deleting the letter A from the end. So if you kind of iterate this, what this results in is that I'm accepting words in reverse. So then, if I don't change anything else, then the definition of that is going to associate to a state of the automaton basically all the words in the reverse language. Okay? Another change I could have done would be, so here I had 0, 1, 0, and then ES or ER and 1. So if instead of, so I keep the same thing as before, so taking the letters from the front, but I now negate all this. So I swap all this around. Let's write it in blue. So I swap all my E's. Can anyone guess what that would do to the semantics? Yeah. So for instance, for the empty expression, before I was getting the empty language. But now I'm going to get the language that accepts everything, because the automaton will look like this. So you can play around with your small step semantics, and that will naturally reflect on your denotational semantics. Okay? So the choice I made for these and the these before, but also for the other examples we saw in the first lectures on streams, I mean, the concrete choice of the coalgebra structure is what then determines the actual behavior of this. We know it's unique and exists, but it's parametric on C. And by slight changes on C, you might end up with things that you didn't expect. Okay? So I wanted to kind of make that remark, which I might not have been very clear on. And there have been a couple of questions about that. Is this clear? Okay, so that's remark one. So the other thing we didn't have time to do is how to connect this picture with Bisimulation and with the proof techniques I showed you in the first two lectures. And basically, this picture, so two states, x and x prime, are mapped to the same element in the final coalgebra if and only if x is bisimilar to x prime, and this bisimilarity is a generic definition of bisimilarity for the functor g. Okay, so we didn't get to see that. And that is in the notes I uploaded on Slack. So there is a generic notion, parametric on G, in the same way that the definition of final is parametric on G for bisimilarity. And then you can show that for a class of functors, these two things coincide. So that tells you that you can use bisimilarity as a proof technique for equivalence of programs. So if you want to check if two programs are equivalent, you can just use bisimilarity. Okay? The other thing I really would like to have shown you is this special type of coalgebras like regular expressions that have the property of being both a coalgebra and an algebra. And that are such that their diagrams glued together. So these are called in the literature bi-algebras. And they are special in many ways, but one of the ways that I like to show in some of the lectures I give on this topic is how the algebraic structure can help you improve the coalgebraic structure, or in particular, the proof method for equivalence. So let me give you an example of what I'm hinting at. If I have a regular expression, I can, using the E and D that I had on the table and using this picture, I can build an automaton for that regular expression. So I can have, let's imagine there's more states around here, but I can have an automaton that in the states has regular expressions like R plus S or And if I have two programs denoted by regular expressions, I maybe build a second automaton here that has R0 star, and maybe it has R prime and S prime, and so on. And then maybe at some point, when I try to prove that these two things are the same automaton, I need to check the equivalence of these two states, R plus S and R prime plus S prime. The advantage of having the two diagrams is that now, when I'm checking the equivalence of R plus S and R prime plus S prime, I can treat the regular expressions that are the name of the states as being regular expressions. And what does this mean? That if in my bisimulation construction, by chance, I have seen that R and R prime were connected, then when I do this check, I can literally delete the prime here, because I know that R and R prime are the same thing. So I can start doing algebraic manipulation also inside the states. So then you have this nice interplay between algebra, that is denoting the states, and the coalgebraic structure that you're using to build a bisimulation. Or in other words, to build a proof that the denotational semantics of your programs is the same. Okay? So again, this would be an extra lecture. But it is, so in the notes that I shared, there is a section called Enhanced Co-induction. And there is a section specific to regular expressions that shows how you can use this method to have more efficient bisimulation constructions. Okay. So the last remark I'll make before showing you CoCaml is about the X. So throughout all my lectures, I said that X is a set. Okay? Now, if you want to use this method to talk about semantics of real languages, you will very quickly realize that sets are not enough. In particular, if you take even a very simple language that manipulates variables, you will want to talk about alpha equivalence, for instance, when you do equivalence of your programs. And so when you want to talk about alpha equivalence, having a set is not enough. But what is kind of nice about this abstract picture is that depending on what are the properties you want to capture, you can vary the type of your base type. So you can move from set, for instance, to something called nominal set, which are sets that come equipped with permutations, so that allow you to talk about names being the same. And then you can basically do this exact same picture. It's just that your base type lives now in a different world. And so you can start with a language with variables and maybe do this picture without alpha equivalence, so you get something that's not super reasonable. So you will distinguish any programs that have different names in the variables. And then without doing anything, so with the same small step semantics, you vary your base category, and suddenly you get for free alpha equivalence. Okay? So there's all kinds of things you can do. When it comes to probabilistic programs, I think Sam Staten is here next week, and he'll probably show you variations on this in which he's going to use convex sets or maybe measurable spaces. I'm not quite sure which version he's going to show you, but when you talk about probabilities, then you need your base types to also have some built-in structure in which you can reason about about the probabilistic aspects of your language. So a lot of the times you will see measurable spaces, sometimes you'll see something called Polish spaces, but basically all of this is a variation on the base type. The rest of the picture stays the same. Okay? Okay, are there questions at this stage or requests? Or is everyone ready to go home?
For these other categories, it can be harder to prove like the existence of the our example. Basically, it was forced. So we would have to check that the diagram actually commutes uniqueness comes for free to go, like defining the function point was.
Right. For a lot of these categories, indeed, the proof of existence and uniqueness is much harder. You're right. But gladly, I mean, I've shown you very concrete proofs of the existence. But you can actually build this Z in a much more abstract way. And you can show that it works for a large class of categories and a large class of functors at once. And so that, if you look in the sort of seminal paper in this area called Universal Coalgebra, then there's a lot of sort of generic results there that one could use. Okay. Arbor, and I'm now in London, so this is really old work. But I just wanted to show you something that I mentioned in the first lecture, and then I talked to some of you during the breaks. And so I want to show you like how some of these things we looked at during this course actually appear in OCaml, and how the support in OCaml is not exactly if you look at the theory I showed you. So here's an example in OCaml defining lists that can either be nil or cones of some integer and a list. So then you can write things like, let rec ones is C of 1 followed by ones, and let rec alt, which is 1, 2, and then alt. So in red, you see the kind of intended meaning. And these are infinite lists, but they are regular in the sense that using the syntax that OCaml provides, you cannot really write much more than ultimately periodic streams. So these are extremely regular and therefore extremely finite in some ways. And, oh, you cannot see that. Okay, maybe if I do that, yes. If I want to define a function that takes one of these lists and returns the set of the elements that occur in the list, one way to define it would be to say, okay, the set of elements of L, I can do two things. If the list is empty, then there's no element, so I return the empty set. And if the list has a head and then a tail, I basically just compute the set of elements in the tail, and then I insert the head into that set. And the insert function takes care of duplicates. So if H is already there, then it shouldn't be inserted again. So the thing I would expect is that the set of ones would be 1, and the sets of alt would be 1, 2. But, I mean, if you run this, this will not hold because OCaml cannot somehow realize that the infinite type is actually very finite and has a representation that is a very simple graph like that. Okay? So yeah, so here are some comments about set. So first thing is that it's not a co-recursive definition, because the solution, so the codomain, is a set of variables, so a set of elements, and that's not a final coalgebra. But it's actually a list solution, and it's a list solution because it's building this set, and you want the smallest set that contains all the elements. So let's skip this. So what we did, and you can find some more material on the OCaml page, we basically changed OCaml to allow you to pass as a parameter to the system a way to solve equations. So if the list is finite, OCaml will just run the function as before, because then it will terminate. But if the list is infinite, it will apply this solver, which in this case we call iterator, and this solver will try to actually solve the equations that you get from the commutativity of the diagram. And those equations, you have a finite number of equations. So if you write your solver in the expected way, then this should terminate. And so let me just show you for this example. So if you have a list, an infinite list, that has 1, 2, and then loops back, then what you know about the result of that function set is that the set associated with the first node, which we call x, has to have the element 1 and whatever y has. Okay? And then you know that the set of y has to have the element 2 and then whatever x has. So you have two equations, and these two equations are basically defining a system that now you can solve. So you can write this, if we write this system in a sort of more mathematical notation, then you will see that this has a solution. So you basically are saying that x is the set 1 union y, and y is 2 union x. Okay? So now you have two equations, two fixed point equations, and in an appropriate domain, as we are here in set, you can actually ask what is the least fixed point of these equations. And you will get precisely that x equals y equals 1, 2. And how do you get that? Well, you get that using standard methods, which is in the beginning, you just guess that maybe it is the empty set. And you replace all the variables by the empty set. And then you check. And then you see that cannot be the case, because the first equation would not be valid, and the second wouldn't be valid. So then you conclude that x must have at least 1. And you conclude that y must have at least 2. So in the next iteration, you check this for the set 1 and this for the set 2, and you realize it's still not enough. So then in the next iteration, you take the union of that, and then you get the set 1, 2 and the set 1, 2, and that gives you the solution you're looking for. But this process is totally, you can automate this construction of this fixed point. And that's what the iterator solver that we had there that's what the iterator solver would do. It would just compute the least fixed point of the equations that the compiler would generate by looking at the definition of set. And you can do a lot of different examples like this, actually. This is another example. And this is an example in which you're trying to do a map on one of these infinite streams. And again, OCaml wouldn't be happy with it. But you could basically use the fact that streams are a final coalgebra, and in fact the solution is a unique solution. So now you have a unique solution, and and you could pass. We also have a solver that would give you this unique solution. And there's all kinds of examples you could do. Let me see if I have one with probabilities. Yeah. So for instance, this is another example. This is a graph that you can represent as a data type in OCaml that is modeling a unfair coin, a biased coin. Okay? This is a known protocol to model a biased coin. And in this case, if you do some computation, you will see this models a coin that will output tails with probability 1/3 and heads with probability 2/3. And if you would like to, so computing this probability, I mean, it's here on the slide, I just wrote the geometric progression. But computing it is, again, because you have a finite protocol with a finite number of states, is again a fixed point equation that you can write down. You can basically just write down the equations that the graph gives you. So you can vary the numbers, but they will always be a solution of a fixed point equation like this. And again, OCaml wouldn't be able to solve this, but in fact you can very easily pass on a solver to the compiler that will tell you how these equations are solved. And in this case is again a unique solution. So we have a solver called Gaussian that basically just performs Gaussian elimination on these equations. Yeah. So this is the same. So this is the code, the general protocol with arbitrary probabilities on the coin flips. Okay, and this is the thing I wanted to show you. Let me stop here. So basically, this is an example of a shortcoming that we found in OCaml, and then by basically using theory that is not only the sort of final coalgebra theory, but also the initial algebra semantics I showed you, and how these things interact, we were able to implement an extension of OCaml that is able to now compute these functions on regular infinite types. And so this is something that I think is kind of, it's kind of surprising that somehow this is not supported natively in OCaml. But on the other hand, if you think how co-inductive types were built into OCaml, maybe it's not so surprising, because in order to be able to solve these equations, we had to basically be very careful with the underlying representation of these infinite things, because you can imagine that you can write the list of ones as just a graph with one node and one loop, but that should be equivalent to a graph that has 3 nodes and then loops back and outputs ones on the way, right? And you want to make sure that your functions somehow don't distinguish these 2 arguments, because their solution is still supposed to be the stream of ones. And that is a lot of bookkeeping that you need to do in order to make sure that the functions that you're defining on these types produce the result that you intend. And therefore, the implementation of CoCaml has, of course, a large overhead that makes it quite slow compared with native OCaml. So anyway, this was kind of the last thing I wanted to show you, because I discussed with several of you in the break. I hope I gave you a glimpse into sort of coalgebraic semantics and the things you can do by using algebra and coalgebra, and by taking an abstract perspective on semantics of languages. And do let me know if you want further references. You can send me an email or ping me on Slack. And I am happy to also take a look at the notes that were taken. And thanks to everyone who took notes in my lectures. And yeah, that's it. Thank you.